In this video we're going to go over 5 examples of conversion from decimal to the floating point and also from the floating point back to the decimal. Now if you're happy with these conversions you can always go on to the next video. But if you decide to work through this video, I suggest that you pause the video and try the conversion yourself, and then afterwards play the video and you can watch my solution. So let's get to it. So we start off with the 0. The 0 means that it is a positive. We then look at the exponent. So the exponent's the next 8 bits. So that's going to be 1 plus 2, 4, 8, 16, 32, 64, 128. So it's 128 plus the 2 plus the 1. So that's 131. So the exponent is going to be 131. But of course we have to take the offset from it. So the offset is going to be minus 127. So that's going to equal a value of 4. So it means that the exponent is going to be a value of plus 2 to the power of 4. So let's move on to the mantissa. The mantissa is from bit 10 to bit 32. So that's going to be 1 upon 2, 1 upon 4, 1 upon 8. So it's 1 upon 16. Plus 1 upon 16, 1 upon 32, 1 upon 64, that's 1 upon 128. But of course with the mantissa we have to add the value of 1. So that's plus 1. So whenever we work this out we're going to have the fraction which will be 16 all upon 128. So 16 into 128 will be 8 times, and then we'll have the 128, and the 1 will be a value of 128 upon 128. So that's going to equal, well that's 128, 138, 137, so it's going to be 137 all upon 128. So that's us got our mantissa. And we're going to multiply it by the exponent, which is multiplied by 2 to the power of 4. So if you put this into your calculator and you work it out, you'll see that this comes to 17.125. So that's us finished the first part. We'll double underline this. So let's go ahead and we'll now do the conversion from the digital, from the decimal back to the floating point number. So we need to change the 17.125 into the fixed point number. So 17 divided by 2 is going to give you a value of 8, and there's 1 left over. And we divide the 8 by the 2, we're going to give it a value of 4, and there's 0 left over. We divide the 4 by the 2, and we get a value of 2, and there's 0 left over. We divide the 2 by the 2, and that gives us a value of 1, and there's 0 left over. 1 divided by 2, well, 2 doesn't go into 1, so we've got 1 left over, so that's the 1 at the end. And we can read it up this way, and that gives us a value of 10001. So let's look at the fractional part. We have 0.125 times the 2 gives us a value of 0.25. So there's no whole part here, so we just put a 0. We multiply the 0.25 by 2, and it gives us a value of 0.5. And again there's no whole part here, so we get the value of 0. We multiply the 0.25 by the value 0.5 by 2, and it's going to give us a value of 1. So there's a whole part here, So we take the whole part up here, and that's us finished. Everything else will be zeros after here. So we would read this one down this way. So we've got the fixed point number, which will be 1, 0, 0, 0, 1, 0.001. Now we have to move the point up to the first one. So we have to move the point 1, 2, 3, 4 places. So that means that the exponent is going to be a value of 4. But of course we subtracted off the 127, now we have to add the 127 on. So the actual value is going to be 131. And 131 is going to be given by 1, 2, 3, 4, 5, 1, 1. So that's 1, 0, 0, 0, 0, 0, 1, 1. So this is our exponent part. Now to get the mantissa, we take the new value here, which is 1.0001001, and we get rid of the first one. So that goes, and it's just left us with 0.001.001. So let's put the values in. We're going to have the 0 for our sign. We're going to have the exponent is going to be 1, 0, 0, 0, 0, 0, 1, 1. And the mantissa is going to be 0, 0, 0, 1, 0, 0, 1. Now all of the rest of the zeros are, all of the rest of the positions are going to be padded out with 0. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's going to be 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 28, 29, 30, 31, 32. So this is our final 32-bit floating point number. And we can check this against the one above, and we can see that it matches. We've got our 0, our 1, and we've got 5 zeros. We've got our 1, 1, and we have the 0001, 001. So we're going to have our 0001, 001, and the rest of the values are all 0. So let's move on to another example. The first value here is a 0, so it's a positive number. The next 8 values are going to give the exponent. Now we've seen these values before. That's going to give you 131. We've got to take away the offset, which is 127. So that's going to give you the exponent value of 4. So we're going to have the exponent is going to be plus 2 to the power of 4. Now the mantissa here is quite interesting, because the mantissa, as you see, starts to repeat after this bit here. So it goes 0, 0, 1, 1, 0, 0, 1, 1, and it continues on along until we get to the final 32nd bit. But this repeating pattern will actually continue forever. And what we're actually doing is we're creating an approximation to the number, and we're cutting this approximation off at this point here. So we're actually going to get rounding errors, but we'll talk about rounding errors in a different video. So let's just go ahead and we'll work out this number first. So we're going to start off with mantissa from here. So that's going to be 1 upon 2, 1 upon 4, 8, 16, 32, 64. So it's going to be 1 upon 64. There's no 128 or the 256. So there's a 512. So there's 1 upon 512. And the next one is going to be 1 upon 1024. And there's not going to be a 2048 or a 4096, but there will be one at 1 upon 8192, and the next one will be 1 upon 16384. 16384. Now this is going to continue on, and what's going to happen is at the end, of course, we have to add on the value of 1. But this is going to tend towards a limit. Now, if we were actually just working this out by hand, we would have a particular value here. But I'm going to give you the actual limit because of course I've already worked out this before. But if you were actually, the computer was working this value out, then it would just round it up to a particular value, and there would be a process of rounding at the end here. So what we're going to have here is the number 1.01875, and the exponent is going to be 2 to the power of 4. So whenever you work this out, you're going to get a value of 16.3. So I've given you the exact answer here, which is 16.3. But if you were to actually look at the floating point representation, or the decimal representation of this floating point number here, you would actually get something like 16.2999937 something or other, because it would be an approximation, and we would be cutting off this repeating value here at the 32nd bit. Of course, if we wanted to make a more accurate approximation to the 16.3, we could use a larger mantissa, and then we would be adding on more of these terms, and it would get closer to the actual limit, which would give us a value of 16.3. So that's enough for that. Let's move on, and we'll go from the decimal back to the floating point binary. So we need to change the 16.3 into the fixed point binary number. So we're going to take the 16 and we'll divide it by the value 2. So that's going to give us a value of 8, and we've got 0 left over. Divided by 2 is a value of 4 with 0 left over. Divided by 2 is a value of 2 with 0 left over. Divided by 2 is a value of 1 with 0 left over, and the 2 will not go into the 1, so we're just left with a value of 1. And we read from the bottom to the top, and that's going to give us a value of 1 with 4 nothings, 0, 0, 0, 0. So that's 1, 2, 4, 8, 16. Now for the fractional part, we're going to have the 0.3, and we're going to multiply it by the 2. And that's going to give us a value of 0.6, and there's no whole part, so we put a 0, multiply this by 2, that's going to give us a value of 1.2, but you can see here that we actually have a whole part, so it means that we take the 1 up and we just leave the 0.2. So that'll be 0.2, and there'll be a 1 here, and we multiply that by 2, that'll give us a value 0.4, there's no whole part, so it goes a 0, multiplied by 2 is 0.8, and there's no whole part, so that gives us a 0, multiplied by 2, well that's 1.6, so there's a whole part, we take the 1 and we leave the 0.6, and we multiply that by the 2, and we're going to get a value of 1.2, so we take the whole part, which is 1, and we're left with the value of 0.2, and it keeps repeating here, so we're going to have multiply that by 2, gives a value of 0.4, and it's going to have a value of 0, multiply that by 2, gives us 0.8, will give us another value of 0, and so on and so forth. So you can see this repeating pattern. We got 0, 1, and we get 0, 0, 1, 1, 0, 0. So again, we read it from the top down. So it means that this part of it is going to be given by 0, 1, and then we get the repeating zeros, 0, 0, 1, 1, 0, 0, 1, 1, and so on and so forth. So it means that the final value that we're looking for in the fixed floating point, fixed binary number, would be 1 with 4 zeros, point, and it would be 0, 1, and then we would have the repeating 0, 0, 1, 1, 0, 0, 1, 1, and so on and so forth. So now we move the point to just before the 1 here, so we're going to move it 1, 2, 3, 4 places, so the point will now go there. So it means that we're going to have the exponent as a value of 4, but of course we have to add on the 127, so the actual exponent is going to be a value of 131, and 131 is written as the 1, 1, 2, 3, 4, 5 and 2 ones. Now the other thing here is that we now have the new value 1 point, and it's 0, 0, 0, 0, so that's 1, 2, 3, 4 zeros, and this point has now disappeared, and we've got 0, 1, and we're going to have 0, 0, 1, 1, 0, 0, 1, 1, and that's going to repeat. And of course we can then get rid of the 1 here, and the mantissa is this value here. So let's rewrite the whole thing out. So I'll just rub this little section out here so we can get space to put it in. So we're going to have 0 for the sign, and for the exponent we're going to have our 1 with our 5 zeros, 4, 5, and the 1, 1, and then the exponent here is going to be the mantissa part here is going to be 1, 2, 3, 4, 5 zeros, 2, 3, 4, 5 zeros, and it's going to be a 1, and then it's going to start that repeating pattern of 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and it's going to do it for 32 bits. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So this is our final answer here. And again we can go ahead and we can compare that to what we have above. So we have our 0, and we have our value here which are 131, and then we have the 1, 2, 3, 4, 5, that's 1, 2, 3, 4, 5 zeros, and we have a 1, and then we have a 0, 0, 1, 1 all the way along, and it finishes with a 0 at the end. So this is correct, and that's us finished this example. So that's us worked through a couple of examples so far, and it's starting to get quite repetitive and the video's getting quite long. So why don't you go ahead and you can see if you can work out these other examples here. Let's say we wanted to work out the 32-bit floating point binary representation of this decimal number 6.25, and you could also try doing it for the number 8.7, and you can also work back the way as well from the floating point binary back to the decimal as a check for your answer. So that's all there is for this video. On the next video we're going to go on and we're going to look at something called denormalized or subnormal values. So thank you for listening. I'll get you on the next video. Goodbye.